Well, a very interesting question, and certainly from my perspective, I think the answer to that would be yes. Because if we consider our five senses, sort of the primary ones which we're taught of since childhood, you certainly can augment those with another four or five, whether they're sense of balance, temperature, pain, amongst some of the others. However, when you think about each of these senses and how we've been wired, if you like, as human beings, I think you really do come to the realization that the inputs that each of these senses can provide us are quite limited from the range of possibilities that are out there. I suppose just picking one of those, a sense of sight. If you consider that the typical human being, the wavelengths of the broad electromagnetic spectrum that most of us can see go from 400 to about 700 nanometers. Now, when you think about things like cosmic rays, which are ultra high frequency, they're like 1,000th of a nanometer, all the way out to radio waves, which are getting towards hundreds, if not thousands of meters, you can see that what we as human beings, just in the sense of sight alone, see as a very narrow sliver of this spectrum. And on top of that, I guess you'd overlay the fact that the way our brains have evolved, I guess, from basic survival instincts, where we're protecting ourselves and looking to feed ourselves, is that the brains are structured in a very specific way to achieve those fundamental, if you like, essential characteristics for survival. This certainly could preclude understanding what we might broadly call the true nature of reality. And certainly even within our own mental context, we have this thought of a notion of altered states, where in those states, we often can find that even with our existing brains, that you're able to have other sensitivities and indeed perhaps different thought frameworks. And the final point I would add there is that if we look at the matter, what we see as matter and energy around us, as best as physics can tell us, it constitutes less than 5% of what comprises the universe. The balance, 95%, is broadly thought to comprise of 27% of so-called dark matter and 68% dark energy, of which we know very little. So hence, with our five senses, I think through or as a result of all of these various factors, we are likely to only have the ability to perceive some very small element of the true reality that's out there. Both dark matter and dark energy are actually fields about which very little is known scientifically at this time. What we do observe is certain phenomena, and some of our scientific theories today require the existence of each of these two, of dark matter and dark energy. However, as to what they are and what they comprise, in fact, is that we don't have any real explanation today. Oh, what an interesting question. And I think certainly this is where you see a confluence between perhaps what some of the great spiritualists have perceived, and where from a completely different approach or different method, science is arriving at some similar types of conclusions. And if we look at quantum theory in particular, I believe earlier on we've spoken about this idea of superposition, which says that quantum states are actually governed by a probability distribution. And therefore, a particular quantum entity can have a probability of being at a particular place or a precise location through a continuum of probabilities. typically these probabilities are in the form of the sort of familiar bell curve, which we would have all seen through school mathematics. And therefore, there is some likelihood of finding a quantum state at a particular point, but equally, there is some probability, and perhaps it could be infinitesimally small, of finding that particular quantum state right at the other end of the universe. So I think it really does suggest that at the most fundamental level of nature, all entities are in some sense connected to the broadest notion of universe that we can conceive. The interesting thing, however, is that as the minute, as best as quantum physics tells us, that you observe any of these quantum states, they collapse. And that leads to its localization to a specific location. Therefore, I suppose if you have the ability in some sense to sense nature without observing it, we might be able to intuit or perceive this continuum. So the collapse of a quantum state is one of the fundamental ideas that underlies quantum physics. And the principle here is that, as we just touched on, if you look at any quantum state, it's governed by this distribution of probabilities of it taking on any value. So if we talk about position, I could be here, or this is now going down to quantum level. So a quantum particle could be here, it could be at the end of this table, it could be with you in India, or it could be at the other end of the universe, governed by this probability distribution. However, the moment I observe that quantum state, that particle, instantaneously this probability distribution collapses and that particle becomes localized, so therefore no longer governed by a probability distribution, but it becomes localized to one of those locations. And this is what's known as the quantum state collapse. Certainly, the concept of entanglement, which again is one of the core ideas within quantum physics, I think touches on very much on this interconnectedness. And the idea here is that two distant objects can become intertwined in a manner that sort of defies classical physics and certainly common sense, our sort of understanding of reality. And as best as we can tell through quantum physics, this interconnectedness is a fundamental property of our universe. One way to visualize how this occurs is that if you consider the most fundamental particle of light, something called a photon, and that splits off into two photons, each of which have half the energy of the original, and they go trucking off to opposite ends of the universe. The surprising thing you find through this property called entanglement is if you observe one of those photons, even though the other one might be spatially very far away, opposite end of the universe, as we just said, you can discern something about that other entangled particle. It should be noted, however, that these states are extremely fragile, and it really has only largely been observed so far at sort of level of light and atoms, so very much at the quantum scale or microscopic scale. However, what we're starting to see is it's now started to become manifest, or science has been able to manifest these phenomena at larger, more macroscopic scales, but still a long way away from human scale. But it is indeed something that has been validated through thousands of experiments. In fact, somewhat amusingly, even Einstein found this idea so counterintuitive that he termed it spooky action at a distance. But irrespective of his skepticism about this particular phenomenon, it's certainly something that is being leveraged. And in fact, quantum computers and quantum internet of the future very much leverage this property to deliver very practical applications. So macroscopic quantum effects are something quite interesting, and scientists have been really trying to reproduce these quantum effects that we typically see at the photonic or atomic level to larger ensembles of atoms, for example. And I just came across some recent research where scientists have managed to bring the motion of two individually vibrating, what they call drum heads, which are actually manufactured out of aluminium on a silicon chip, into an entangled state. So it's the first time we've actually seen entanglement occur at a scale which is starting to approach human scale. And I understand these two microscopic drum heads were about the width of a thin human hair. So by far the largest macroscopic ensemble of quantum states which have exhibited a collective quantum behavior. So although it's not a field that I have any great knowledge about, but string theory certainly posits that the fundamental constituents of the universe are actually one-dimensional strings rather than point particles as perhaps previously we've considered in quantum mechanics. And what they suggest is that what we perceive at the sort of most fundamental level of nature as particles are actually so-called vibrations in loops of string. I imagine this is a mental construct that they've developed to help us visualize this characteristic. And each of these strings is vibrating with its own characteristic frequency, giving rise to the distinctive properties like mass and charge and so on and so forth. The primary goal actually of string theory was to join the laws of quantum mechanics, which are, if you like, the laws of the very small, with the laws of general relativity, the laws of the very large, into a mathematically consistent framework. I think there's been, as a number of you might be familiar, a search has long been on for what we call a grand unified theory, which would pull together these multiple specific theories into a more complete whole. So that's what string theory attempts to do. And one of the things that it does suggest is that there are many extra dimensions beyond the obvious ones of length, breadth, depth. But we actually don't experience these because they are bunched up into very tiny spaces in these strings, which are beyond our perception. So very interesting. They've given a term called a brane, B-R-A-N-E, which is this generalized notion of a point particle, but associated with these higher dimensions. Within that context, there is this also thought of the multiverse. And this idea is that the universe, or these multiplicity of universes, actually comprise the entirety of what we know. So space, time, matter, energy, information, and the physical laws and the constants that describe them. And so these different universes could be called parallel universes, other universes. You may have heard the many worlds interpretation also mentioned. And this many worlds asserts that as you have this collapse of the wave function, which we just touched on, that at each point that there's such a collapse event, that there a new branch, if you like, or new branches of the universe are created, which capture the multiplicity of outcomes of that. We might travel in one branch and have visibility only into that, but the many worlds interpretation suggests that every possible outcome at each of those quantum events is a new multiverse that is created. So I wonder if you recall the Schrödinger cat experiment, which we talked about, whereby this cat was in a box, and this was a thought experiment that the famous scientist Schrödinger conceived in the 30s, and whereby the cat was in a box with a radioactive source in there, and if that source was triggered, it would release something which would destroy a vial of poisonous gas and kill the cat. However, we don't know when that nuclear event or the emission of the particle would occur from this particular atom. So Schrödinger posed the question that, well, when the box is not opened and you don't know if the particle has been emitted, and therefore whether the vial of poison has been broken or not, how do you know if the cat's dead or alive? In the multiverse model, every single possibility at every instant of time that could have occurred there all exists out there. I think, interestingly enough, I need to go back and refresh my knowledge of this, but there's Brian Greene, who perhaps you may have read a book or two from, and he has this interesting idea of visualizing all of these multiverses as one big static. So every possibility of everything that exists in terms of alternatives all exists around us now. In our lives, we're traversing a particular trajectory through all of those different possibilities, but all of them exist at the same time. So kind of bends your mind a little bit, but I thought it was a very interesting thought. Indeed, probably the idea from the quantum world that provides the closest parallel to this is this idea of wave-particle duality and the interchangeability of form. So all of us from our school days would remember, of course, the famous equation from Einstein, E equals mc squared. So that really talked about the equivalence of energy and matter. And that, in fact, was in some senses captured by an interesting experiment that was done in 1801 by a scientist called Thomas Young. And this is a so-called double slit experiment, whereby he had hypothesized that the way that light behaves, it moves as waves. And much like if you drop a pebble in a pond and you see all the ripples extending out from where the pebble was dropped, those are waves through the water that you're seeing of that energy propagating. So what he did was to try and demonstrate this was set up a little light source, and then he had if you like, a barrier in which he had two little slits. Now, as the light propagated from the source, it went through the two little slits in the barrier, and on the back he had a screen. And as you'd expect, if light was in wave forms, as it hit each of the slits, what you would see is small semicircles of those waves then continuing out from the two slits on the other side. And when they hit the screen at the back, what you would find is where two waves were cresting together, that you'd get what's called reinforcement, so that you should get a lot of light. Whereas when waves were out of phase, as we call it, or out of sequence, we had one trough hit one peak, they should cancel out and you should get a dark pattern. And that's exactly what he saw. So even though there was a single light source and you had these two slits, then on the back screen, what you saw was this interference pattern, which was a periodic repetition of dark light, dark light, dark light bands. So that, to him, proved his hypothesis that light was a waveform. However, the interesting now complication comes up is that if you add an observer to either one of those slits or both of the slits, the waveforms disappear. And what you get behind the two slits, if you want to picture in your head a sort of triangle, which goes from the light source, and then the other two ends of the triangle are the two slits through which the light is passing. What you found was it started acting very much like particles, and the interference pattern that was on the back screen disappeared, and what you got was just two bands of bright light directly behind the slits in line with the light source. So this was very confusing and not easily explainable until the ideas of quantum physics started coming around in the early 1900s, and something that has now become very well established, the so-called wave-particle duality principle, where matter can exist both in solid form, if you want to call it that, particle form, but equally in wave form. Certainly there have been many more complex experiments that have taken even more complicated three slits and complicated pathways, but that have continued to support this idea of interchangeability or duality between the wave form and the particle form of reality, I guess we would call it that. And the only other thing I would add is that there's some interesting research that's emerging, which we had briefly touched on previously, was about this potential for wave-particle information triple. It's very early days, but there is some early work going on that suggests that perhaps there is the interchangeability between waveform, particle, and information. Indeed, the observer actually has a very important role in quantum mechanics, and a fundamental tenet of quantum physics is that act of observation, no matter how subtle or indirect it might be, affects that which is being observed. And as we were just discussing, there's no doubt about this. It has been validated through thousands, if not tens of thousands of experiments. And we talked about this probability distribution of quantum, which governs quantum states. And the second, or the instant, I should say more correctly, that an observation occurs, as best as we can tell, this probability distribution governing any quantum measurement collapses and takes on a very specific value. And it's a very specific value, sorry. But what I did want to say is that there are these fundamental limits on how well we can know any pair of related values in the quantum world. So a typical one, such as position and momentum, or position and, loosely speaking, speed of a particular particle, if you want to know both simultaneously, the laws of quantum physics suggest that there will be a minimum level of uncertainty in that joint measurement. And that's something which is governed by the so-called Heisenberg's uncertainty principle. And so it seems that there is an absolute limit to how precisely we can actually know the nature of reality. This is an interesting area, a bit of a conundrum, I would say, for physics. And again, it ties back to the entanglement, the principle of entanglement that we touched on earlier. And whereby, as best as we can tell, there appears to be almost instantaneous communication or linkage between pairs of entangled quantum entities. So again, as physics would conventionally have us believe, that there's a fundamental limit on any form of communication or motion, for that matter, which is governed by the speed of light. However, in entangled states, we are seeing, as best as we can tell, that when you do something to one of those entangled states, and even if the other entangled state, the pair, is very spatially distant, they seem to have this instantaneous ability to affect, or I would put it in quotes, communicate with one another. And I believe you touched on it, that there have been a number of experiments that have demonstrated this effect, the so-called idea of quantum teleportation. So some of the experiments that we have seen to date have demonstrated that you have two entangled photons which are spatially separated. And if you measure a characteristic of one of those photons, you can immediately know something about the same property of the other entangled photon, as you can say. So I think, we are a long way away to being able to demonstrate this at macroscopic scale. So the phenomena that we see in movies of persons or objects being teleported, of course, is way into the distant future. But certainly at the quantum scale, a number of experiments have demonstrated this effect. Well, the concept of time, as we know it, and as explained by Einstein's theory of relativity, is intimately tied to what we call the observer's frame of reference. So that really a frame of reference for a particular observer is the observer, some kind of a coordinate system, right, whereby you can put an X, Y, and a Z location for every element of that, and a clock. However, the interesting thing that we do find is that if you have a relative velocity between two observers, that the time, if you like, can either stretch or dilate, stretch or shrink as a result of that relative movement between the two observers. It can also be affected by gravitational potential. So if you have a very large gravitational potential around either one of the observers, you will see a difference in their concept, if you like, or their experience of time vis-a-vis what the other observer, who was perhaps not as affected by that gravitational force, could see. So I think it certainly brings into question the I suppose human experience would just suggest that time is equal amongst all of us. When you do start looking at larger scales and at velocities that start to approach the speed of light, what you find is that time is actually not constant, and it very much depends on the observer's frame of reference. Certainly, I think there's several things one can draw upon, and perhaps I'd offer you two examples from the mathematical world and perhaps two from the world of physics. So one, which is an interesting one, is the so-called Fibonacci sequence. There's a thinker who's called Leonardo Pisano around about 1170 in Pisa. And he came up with this interesting sequence of numbers whereby you start off with a 0 and 1 as the first two numbers in the sequence, and then every subsequent number is derived as an addition of the previous two. So to get the third number of the sequence, you would add the 0 and the 1, which would also be 1. So the sequence now becomes 0, 1, 1. Then to get the fourth one, you would add the preceding two. So numbers 2 and 3, which were both 1, and therefore they add to 2. And if you carry on the sequence, you will get 0, 1, 1, 2, 3, 5, 8, and so on and so forth. The interesting thing to note is that if you look at the dividing any number by its preceding number, you get this ratio, which is referred to as the golden ratio, which is approximately 1.618. Now, what you find is, interestingly and somewhat bizarrely, in nature, you find this kind of pattern occurring quite frequently. In fact, the famous astronomer Johann Kepler found that many trees, the leaves on their stems were aligned as this pattern. So if you can imagine that there's a stem and there's a leaf growing in a particular direction, and you twirl around and you get the next leaf, it's around a little bit. And then eventually you'll find that a certain number of leaves up, you come to one which is aligned with the original leaf. And what he found was that you could, in a range of different plants, find that after 1, 2, 3, 5 iterations is where you found this alignment occurring naturally, exactly in the same sequence as what the Fibonacci sequence would suggest. You also find in flowers, for example, the number of petals on them are often aligned with the same Fibonacci sequence. So 3 petal flowers, so lilies and irises would fall into that category, or 5 Panacea rose hips, or 8 Cosmea, and daisies, 13. So as you can see, exactly that sequence, 3, 5, 8, 13. Quite odd and strange, but we don't know why, but we do see these patterns occurring in nature. Interestingly enough, it seems somewhere this is wired into our brains as well, because as human beings, we find a certain ratio of proportions particularly attractive. And that ratio turns out to be the golden ratio that we just talked about, the 1.618, which is if you take any number in the Fibonacci sequence, divided by its preceding number, you get that. We find that for people, for example, that we consider attractive, many of their proportions would be in this ratio. And one example of this is in your face, is that generically and irrespective of race and color, that we find typically people who have this golden ratio between the length of their face and the width of 1.618 as being particularly attractive. As somewhat of an amusing side note, a number of plastic surgeons, I believe, are using that to guide their work and achieve this golden ratio on the people that they're working on. So that's the first example from math, which is Fibonacci sequence. The second would be the fractal theory. So this is really interesting, I guess it's comprised of these complex but never-ending patterns, which are described as being self-similar at any scale or across different scales. And sometimes this is even described as the geometry of chaos. And the idea is that if you have some simple process and you iterate it through a loop many, many times, that same pattern that you see at a small scale starts to manifest itself at bigger and bigger and bigger scales. And examples of this could be trees. So if you look at a tree at a macroscopic scale, you see the branches and the leaves coming off it. Then you zoom in on a particular branch, you see the same pattern repeat itself. And if you zoom in on some sub-branch, more than likely you'll see that again. But the same idea can apply to rivers, coastlines, mountains, clouds, snowflakes, etc. And it's the same idea. You look at it at a particular scale and you see some kind of pattern, but you zoom in on one part of that pattern, and when you magnify that out, you see the same pattern again, and you do it again and again. And it's basically this idea that you go down a very large number of patterns, but the same general form which you observed at the larger scale repeats itself at the smaller scale. And while it's seems contradictory, right? Because it looked like it's random at casual glance, but there is some structure at a deeper level. Perhaps in some ways it's like our own lives. So that's a couple of interesting examples from the world of mathematics. If we look at the world of physics, I think we had touched upon this idea of entanglement, and particularly macroscopic entanglement. So whereby we have this connectedness between entangled states over vast distances. And it is quite possible that we do see this connectedness being exhibited and manifest through the universe on some grand scale. And really that if you like, as was in the question, that part of a grander, larger whole. The second thing which comes out of quantum physics is this idea of the Higgs field. So a number of you may have heard about the so-called God particle or Higgs particle, which was hypothesized a couple of decades ago, but only as the new super hadron collider was constructed that we were able to experimentally prove the existence of this particle. And what Higgs theory suggests, particularly through a Higgs field, is that there is this field through which these Higgs particles arise, which spreads throughout the entirety of our universe, which would very much suggest that it is one continuum of energy, if you like, in every region of the universe. And this particular field is accompanied by something called the Higgs boson, which is what was discovered by the CERN. And this is the particle that exists within the Higgs field, and which through it's continuously interacting with all the other fundamental particles that we previously looked at, such as electrons or bosons or photons. And it is the particle that through these interactions is supposed to give mass to those other particles. It's also been referred to as I mentioned, as the God particle. And this, in some sense, would support this idea that the entirety of the universe as we know it is one continuum of a single Higgs field.